Got it.
Start. It's almost finals week, so I'm not expecting too many people to be present. All right, guys, can I get some silence? Only because my mic is on and they are going to get a feedback loop if you also speak. Anyway, today is the last lecture for this Introduction to Deep Learning series. And today I thought before I let you guys go, I will talk a little bit about state of the art in artificial intelligence. If you remember, we started with understanding what transformers are and then going back and trying to get a hands-on view of how to use an open source model like Llama. And also we talked about fine-tuning the model. So I will get that in a second. Somebody is not muted because I can hear my own feedback on Zoom though. Okay, as long as everybody in the Zoom call is muted. As a reminder, we always have our stuff, slides, recordings, etc. stored on Wiki. You guys know this. I'll do a quick review of what we did last week or the week before Thanksgiving when we met. So first, we were asking the question, how do we get a hands-on tool to work on huge data sets and huge computing power? And also, more importantly, also have a Jupyter notebook like front end sitting on top of it. Our immediate choice was Azure. Like HPC, of course, on campus gives you the high performance computing, but that also means you have to push everything through a command line and you cannot debug it then and there. So hence we introduced you to CyVerse. You know, the other paid options, of course, if you are rich and can pay for it, are AWS and AWS SageMaker, Azure, or you can just Google any of the high performance computing cloud. Also, I wanted to introduce Jetstream. I think I briefly mentioned this earlier. Jetstream is basically, wake up, skip verification. Basically, long slide, now push. All right. If you click on that link, you'll go here, which is kind of CyVerse, but on steroids. When I say steroids, CyVerse, you can get a GPU, maybe one GPU. Here, you can get the state-of-the-art GPU, anything you want, including like the A100 latest one. So you just have to go there, apply for a Jetstream allocation. You write a one-pager, especially if you're students. I was told you get this in a day. And this is funded by NSF, where for the same reason, we want an open source high-performance computing cluster for education. Okay. And also, I don't know if you guys have seen this before. This is another tool I want you to be familiar with. Like you right now have all the skills you need to figure out what LangChain is on your own. Kind of not a high performance computing, but this is again, let's say more sorry, let me go to the documentations. They call it framework for developing applications powered by large language models. The way I call it is, this is sitting one level of abstraction above the code we were writing on Python. So, I mean, instead of Hugging Face library, they help you like directly click, and do the stuff. Your choice, how you want to play around with it. Again, this is all levels of abstraction and how much freedom each of these gives you. So far, your closest freedom is code it up yourself using Hugging Face. Play around with this too. So just wanted to throw it out there. This is the agenda for today. So we are going to look at the state of the art in AI or deep learning, reinforcement learning, along with the reinforcement learning human feedback. That is exactly what ChatGPT was trained on. Then we'll talk about stuff like retrieval augmented generation, which is people have, since ChatGPT came out, people have been coming up with these interesting ways of enhancing or extracting the maximum possible information from a black box model. Some of them are retrieval augmented generation and chain of thought reasoning. Then I'll quickly touch upon multimedia. Basically, in the entire lecture series, you have only been looking at language. Of course, all the state-of-the-art large language models are built on language, but people have started extracting their power to utilize multimedia like video and audio. I'll talk about how they have been doing it at this point. And also I'll talk about my research on quantum NLP, which is the next level of artificial intelligence known as quantum AI. If we have time, I will go through fine-tuning a Llama. So first I thought I'll show you guys the slides of fine-tuning a Llama. The code for fine-tuning a Llama is already up there in our repository, CyVerse one. And in fact, these are a few links which I had used to refer this. So, I mean, like I said, at this point, you can run this on your own. You'll understand most of the stuff. If not, go to these links. But since it's the last class, I did not want to spend time too much on giving you a fish or fine-tuned fish. I would rather teach you how to fish, and especially how to fish tomorrow. Like, you know how to fish today, but are you ready for tomorrow, right? So let's start with what is reinforcement learning. Reinforcement learning, the way I want to start this is, if you remember the cruise control example we always have been talking about, the whole idea is, we start with the machine or the car is at a speed of 45, and you set the cruise control speed to 50. It checks the number 45 with 50, goes on a feedback loop, and realizes, oh, I'm 5 below, so let's increase it 1, feedback, back propagation, etc., etc. So this is like a rough, back of napkin, paper napkin kind of diagram. Same thing, we have initial speed, you compare with the target speed. How much is the difference? Lower, equal, or higher? If it's equal, don't do anything good, just stay in that speed. If it's lower or higher, give a feedback into the initial speed. Now, remember, deep learning is kind of sits on the same thing, but there's a slight difference, right? So here, I don't know if you can see it. We start with, this is the cat and dog example, right? What does it say? Oh my God, even I cannot read it. Has whiskers, yeah, sorry. Okay, yeah, so the data says this thing has whiskers, barks, and meows, a bunch of things. Some might be cat, some might be dog. So now the deep learning model predicts a random value, compares with the gold value for that picture. Let's say it's a dog, right? So let's say initially it predicts it's a cat, but the gold value is it's a dog, right? How much is the difference? The same feedback loop, right? So this is how deep learning fundamentally works. But remember, there is no modification to data, in the sense you are stuck with the 10,000 or 1 million data samples humans provided. Like, you cannot touch if this data doesn't look good. It has whiskers, it should really be having, it barks, right? So the agent has no control over the data. And that is a question reinforcement learning was asking. Why not give power to the agent also to modify the data? Like, you're not stuck with a bunch of gold data, but you can also, you're open to these minor details of has whiskers, has 4 legs, has hoofs. I mean, you can add has hoofs, right? Or it's already there. We are opening up these combinations of permutations and combinations to the agent. And then does the feedback loop proceed the same way? The only difference is we bring in all these things called rewards and actions. It's just the same, roughly this is the same idea, like training a dog. If it gets the right answer by the right combination of features, a dog has barks, has 4 legs, doesn't have whiskers, then it gets a reward, and the agent really gets a reward for what it's doing. And just the exactly same as your state-of-the-art deep learning methodology, but now it's just the feedback loop is also involving the modification of the data. So that is one of the basic basic ideas you need to understand about reinforcement learning. And I'll quickly introduce how does ChatGPT do it. It does it in 3 steps, right? Remember, right now, we started with supervision. Supervision simply means, we already have the data and there's a gold label. So here's an example. The label is explain reinforcement learning to a 6-year-old, right? And a labeler, a human being, demonstrates. So these are all gold labels, kind of equivalent of bunch of features of dog, and the human labels it as dog, right? Okay, so the human says we give treats and punishment to teach kids, and that's how you teach. That's a kind of the same thing as reinforcement learning, right? First and foremost, this data is used to fine-tune GPT with supervised learning. Remember, by the time we get to GPT, it's already seen all these millions of data from the internet in, if you remember that regressive or auto-generative format, which is, this is blank. This is, he tries predicting this is cat. Okay, then when it gets it right, it moves to, this is cat, goes back into the feedback loop. After all that, they do this fine tuning here. And then the second step is collect comparison data and train a reward model. A prompt and several model outputs are sampled. So here's the prompt again. It gives a bunch of its own, the machine gives a bunch of its own predictions for how do I explain reinforcement learning. Again, a labeler ranks it. Like, In fact, I just introduced you to RLHF, Reinforcement Learning Human Feedback. The only interesting part here is there's a human sitting there and constantly going through every single prediction of the model, labeling or giving it a reward based on what is a good prediction. And remember, the definition of good is completely qualitative. Like, if you think about it, only a human understands what another human says. Only another human can decide what is good. And what is a good explanation, right? So this was so the truth is you're now dependent on the power, the understanding or assimilation power of the labeler, sure, but it seems to work. Everything else is optimized. This policy is basically like it's trying to find that nice kind of a learning or weight. And then again, you have a new prompt. It write a story about authors. Just the same thing, generates an output. The reward model gives it an output. So it's just a same feedback mechanism. But the only difference is human feedback comes into picture. Quick comments on what is retrieval augmented generation. It's simply this, right? So when you start with ChatGPT, or let's say this model was never trained on your emails. Now you ask this model, what was the name of the movie Chris emailed me about last year? And ChatGPT says, sorry, I don't have access to any specific information about emails. Now you fine tune it, or more interestingly, you actually, instead of fine tuning, just open up an SQL query database to your emails. And now you ask the same question, what was the name of the movie Chris emailed me about? It goes through your emails. And of course, it says, emailed you, the movie Chris emailed you about was fall, right? It opens a new can of worms as to like, where is your data sitting? Why do I want to expose my personal emails to a large language model? Different discussion. Just a deeper look, same thing. 2 is basically your original enterprise app, AKA example ChatGPT. Embedding model, you provide the documentation, retrieval, and ingestion. Both of them feed in together. The same stuff as before, potentially prompt tuned, or basically this is your local LLM tuned on your emails. So the examples are like, hey, we can use this AI model supplemented with a medical index. That way you could be a great assistant for a doctor or nurse, and that way your data is hopefully still staying in your local hospital. You don't want personally identified information to get out of the hospital. Same thing as financial world, analysts could benefit from an assistant linked to marketing data. That's a quick introduction of what people have been doing on GPT. Another thing people have been doing is chain of thought, which is simply said like this. You might have seen these examples before. So when this is like a known example how GPT was failing initially, or ChatGPT was, when the person asks, Roger has 5 tennis balls, he buys 2 more cans of tennis ball. Each can has 3 tennis balls. How many tennis balls does he have, right? The answer is 11. It gets the first answer right. So it's learning from that answer. Now you try asking it, instead of tennis balls, you ask about apples, or it goes confused. Like, it's completely confused. It cannot fine tune or prompt engineer that fast. So it gets a number wrong. I'm going to believe them when they say the number wrong. I don't want to show my addition skills and tell you it's actually 26. Anyway, on the right side, you show them explicitly the chain of thought. Why did you multiply, or why did you add 5 plus 6 equals 11? Because that's how you can explicitly, now you ask it to tell this explanation. And once you're prompting, kind of telling the agent like, hey, can you explain? Like, usually at the end of this, can you explain the steps? That's like they add the prompt. And once we do that, it was found that the machine slowly understands. So, if you take a step back, like I always say, always look at the big picture. We were talking at one level of granularity deeper with the AI model. Once you stepped outside or stepped inside, however you want to look at it, and ask the model to explain how did you get there, it answers the next question correctly. That's it. This is how people have been thinking of all this chain of thought prompting. Next is multimedia, right? So all this while computer vision and music, everybody was trying their own models, and then suddenly GPT took over. So people started asking, why not use the power of large language models to learn transferable visual models, right? And the basic idea is something like this. Here on one side, let's say you have an image of Pepper the Aussie pup, and the caption also with it, Pepper the Aussie pup. So you give it a text encoder, like a typical embedding-based mechanism. You take the picture to an image encoder, and you create a mapping. So you learn, this machine actually learns this mapping between each of these encoding. It's like a heat map, right? So given these 256 bits of floating value and of the image, 256 values of text embedding, what can we learn from it? And next is on the other side, we create a dataset classifier from just the label text, right? This is just like plain car dog, photo of a blank, text is learning that. And that is used along with the one we just learned for a zero-shot prediction. So basically, short answer, they just added a new layer of mapping between image and text, and the text was able to like correctly predict. Like it was trained on 1 and 2 and 3. It was used for prediction of a new dog, and it says, hey, that picture, you didn't even give me the caption for the second picture. This one here on number 3, the machine says, yeah, it's a photo of a dog. So this is how people have been leveraging that part of combining image with the huge knowledge LLMs have been learning. Okay, so let me get into the more interesting part. Hopefully it's very interesting to me, might be interesting to you after, I hope so. So here were some experiments I did. Okay, so this is my bread and butter, my favorite topic, quantum natural language processing. So let me start with this example. Here are 2 sentences. Bob likes warm beer and Bob doesn't like warm beer. And I ask you, like as a user, do these sentences agree, disagree, or are neutral to each other? So of course you tell me they disagree with each other. Second time, okay, this particular problem is known as recognizing textual entailment. You don't need to know this. This is also used in fake news identification. This is all my PhD thesis. Now, second time, what I did was I took the first sentence alone, Bob likes warm beer. I did not get a second sentence. Whatever we saw, Bob doesn't like warm beer. If I ask you, right? If I ask you tell me if these 2 sentences agree, disagree, or are neutral to each other, you're going to be confused. Like, it doesn't make sense. You're not giving me the second one to compare with, right? However, I asked the same question to a state-of-the-art AI model, and it immediately responded, disagree. So there is something going on. That's when it triggered everything. Right? There's something going on with this model. It's really learning from the previous question, or more interestingly, it's learning it's not really understanding what it's learning. It really is grabbing the straws. It's learning some very subtle patterns. Clearly, we don't understand because it's showing us, hey, this is a good number. Like this number is mapping with other number. And we are hoping it's learning. But then these are the kind of experiments which show that, it probably is not learning anything. It's just looking for the word Bob likes and warm beer and just replying disagree. In fact, there is this interesting experiment people suggested. I know I introduced you to Llama, but Llama is, the sad truth is it's not at par with GPT models. So here's an experiment. Once you go back home, open your model, the chat window we created, open GPT on one side, and ask the same question. The first question is, how do I change oil in a Nissan 2023 Nissan, right? It will give you, hey, blah, 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 blah. Here's the way to change oil in 2023 Nissan. Both these guys will kind of give the same answer, Llama and GPT. Now ask the question, how do you change oil in a 2023 Tesla? Llama gives you the same answer, while GPT says, oh, Tesla is an electric model. You don't need to change oil. Right, so it's really looking for, these are all subtle examples of it's really probably learning all these weird patterns from what you ask, from what it has seen before, because we don't know what it has seen before, which is the whole of internet, petabytes of data, right? To prove this, what I did was I took only like 100 data points, right? So 100 data points like this: Bob likes warm beer, Bob doesn't like warm beer, Bob likes to smoke hookah, Bob doesn't like to smoke hookah, agree, disagree, neutral. So I provide all the right labels. And I trained, like from scratch, trained 2 state-of-the-art AI models. So I need to make a comment on from scratch. If you realize, like in the last 2 or 3 years, we don't have any models which you can train from scratch, because everything you get are pre-trained, like Llama or GPT. It's trained on everything on the internet. But what if you said, I don't care about internet. I don't have resources to run all these models. So before these LLMs came out or took off, so this is what people were doing. Like, take a BERT model, BERT-based transformer-based model, train only on your data points. Like, I don't care about everything under the sun or Wikipedia or internet. I just want these 100 models trained. So Roberta Large was the last, is still the last. You can Google that, not Google, you can Hugging Face, go to Hugging Face and find that this is the last biggest models, which you can completely train from scratch, or one of the BERT-based models. But because if you click Llama, it says, oh, here's a pre-trained model. You can fine tune, sure, but we're not going to tell you, like, give you open from start from zero. So I took that model, gave it just 100 data points and said, hey, predict on this new example, does Bob like warm beer or not? Both these models, like Roberta Large, and this is another state-of-the-art model, just tanked in accuracy. Like these models, remember, are like well known for 99.99% accuracy when it's trained on huge amounts of data, clearly your GPT example. But with just 100 data points, the model is like, I have no idea, man. I don't know what you're asking. 100 is like too small a number for me to find some amount of patterns. So remember, we are going back to this subtle pattern idea. It's probably just learning that, Bob and warm beer occurs twice or n times in a 1 million documents. So every time I see Bob and warm beer, this is the answer. So why does this happen? So like I said, it's an answer of why we need whole amount of training data, right? So like if you see GPT-4 is close to 1 trillion parameters, like that's only the weights of the neurons, like 1 trillion neurons, but the actual data it trains is on petabytes. So you throw that amount of data at anything, it's going to learn all the subtle patterns. I mean, these guys cannot, agree or disagree, cannot comment or decline. They cannot prove it other way, right? They cannot disagree or fight my argument that they're probably not really learning anything. It's just learning subtle patterns. The jury is out one way or the other. Here's an interesting, AI models, which are, my question I've been asking is, are these models really learning language or are they just winging it, right? So Calvin Hobbes asks, are you making any resolution for the new year? Like, yeah, I'm resolving to just wing it and see what happens. That's what we do anyway. So let me put a pin on it and ask this other question. How do humans do language acquisition, which is a fancy word for saying, when you're a baby, how did you learn the first language, your mother tongue, your native language, right? So we learn from a lot of things. If you think about it, we learn from meaning, we learn from grammar, like we use the meaning to build up things. We also, of course, learn from context. Remember the bank example? And we also learn from actual real life examples. Slowly, it's a very slow learning process. So, I mean, clearly I'm not the one who came up with this, right? Because these were like two major schools of thought in AI or NLP from almost like a century ago. Like people knew this, right? If we are training machine to understand language, there are two ways of doing it. So learn language from the context is essentially what AKA LLM, which is you throw a huge amount of data at it and it's hopefully learning from the context, or it's learning from all the words surrounding a given word. The other school of thought was, we should learn language from meaning and grammar, just like human kids learn. In fact, these two school of thoughts have parallels in all disciplines. They are known as Scruffy or NEAT, the two schools of thought. It's exactly what it says. The Scruffy school of thought is what like computer science, for example, belongs to, which says, get shit done. We don't care. We don't understand the math. Doesn't matter. We don't care how, deep mathematical equations go underneath the computer. We just want to get things done. The NEAT guys are more like the physics and the math guys saying, oh, no. We are not going to do anything until we completely understand from scratch why it's doing what it's doing. And of course, like until 2010, the whole world was at a NEAT level. We are like using linguistics. We were using a lot of mathematical formula. If you know Noam Chomsky, there is this whole idea of universal grammar, kind of saying that all languages come from one single language and follow the one single grammar, etc., etc. Extremely math, right? So from 2010, like until then, this linguistics department was a purely theory department. Around 2010, almost all linguistic departments came up with this new sub-department known as human language technologies. They slightly started switching to the Scruffy model, which is saying, hey, looks like all these large language models are doing something. And that's the large language models were exactly the context-based models, right? They were learning from that. And all these linguistic departments started offering Scruffy courses, which is like, let's take an LLM, let's take BERT, let's take transformers, work with it. So So there was a paradigm shift. And I just want to, like, you've probably seen this example before in my other lectures, right? So this was the first school of thought, which is, hey, if I tell you the word bank, does it mean a financial institution? If I tell you I'm going to the bank to withdraw some cash, of course, you know I'm talking about a financial institution. And then if I tell you I'm going to a river bank, you know we are talking about, and say I went to the bank and did some fishing, then you know I am talking about the river bank, right? And the school of thought there is learning language from context. What it does is it takes this entirely well-structured thing known as human language, breaks it down into something known as bag of words. And all it does is counts the frequency of words, like how many words, like let's say in this case, the word satirical. It doesn't look at the meaning of the word satirical. Instead, it says, let's only look at the meanings of the guys around it and learn that pattern. This is the same thing I mentioned earlier. Like, it's probably just memorizing 3 words: Bob likes warm beer, 4 words. And it's just saying every time these words occur together, the answer is agree or disagree, whatever, right? The question then is learning language from context enough to learn meaning of a sentence, right? Is it a good idea to, or even worse, right? Is it a good idea to break down a sentence, which is a well-established combination of meanings, and then we are trying to grab straws using context? So these are the questions I am asking, right? And these are the questions people have been asking in my school of thought. And the question is, if you have to, and the point is, if you have to learn meaning from context alone, of course, it makes sense that you need to see tons and tons of examples before you arrive at the meaning of a word, because you're not learning the meaning of a word from the meaning of a word or the definition of a dictionary. That's how humans learn, right? Remember when your mom says, hey, let's go to a bank, you ask the mom what a bank is, and the mom explains this is a bank. So you have a mental model that forms in your head. Or even, we look up, when you hear a new word you don't understand, either you ask people or you look up in a dictionary for the definition of it. However, for these large language models, the lookup dictionary is only 1 in 1 petabyte of data points. It is not giving extra information to the meaning part of it, of course, right? Clearly, that's not how humans learn language. And of course, it makes sense, like GPT kind of models need all these huge amounts of data because you're learning only from context. Meanwhile, the second school of thought comes from this, Ludwig Wittgenstein, that's a philosopher, who says, context is not meaning. Meaning is context. Basically saying that, the same idea, right? Bank has a definition, which is not decided by let's go to blank to withdraw some cash. That meaning is independent. And that is what you build upon. So how do humans learn a language? We start with meaning of a word. We build a sentence with this flow of meaning. And then you keep your mental model collapses into different ideas, right? Say bank. So initially your mental model was bank is something where you get cash. Only until you see the new example, let's go to a bank to get some fish. So now you really need only 2 examples, not 3 trillion or 3 petatrillion, whatever the big number is, right? So humans, in a way, are learning meaning of a word and building a sentence up with the flow of meaning. So remember, once you have all these independent words, you as a baby slowly start putting them together. And it's more, your mental model of a bank is very, very small when compared to the mental model of let's go to a bank. Say your dad and mom are called Alice and Bob. Initially, that mom is Alice, dad is Bob. And somebody tells you Alice loves Bob. So your mental model of Alice and Bob is smaller than your mental, it coalesces together to become the big mental model of, oh, Alice loves Bob, mom loves dad. So if it's a different way of humans learning. This goes back to our initial question of, if you want an augmented AI, augmented intelligence as AI, sure, GPT is doing great. If you want a copy of human intelligence, I don't think it's anywhere near the copy of human intelligence. Now, another putting a pin there, right? And I'm going back to one of these things I keep, harking about. Remember, we are also in a continuous world where we have been using discrete tools to understand the continuous world, right? Humans couldn't understand what a line is, so we started dividing it into small pieces, then integrate it. So you see the pattern, right? We are taking a big sentence, breaking it down into small pieces, and grabbing the straws. Does work well, but you should always step out and look at the big picture. In fact, these are the fundamental gates based on which your computer runs, your classical computer. But why are we stuck with this, right? Human world is not 0 or 1. Human world is a continuous spectrum. There is no true or false. You ask a question, everybody says it depends, because there is no right or wrong. There's no gray, black or white. It's always gray. We are just stuck with it because somebody invented transistors. Oh, and transistors can only do zeros and ones. Same thing in maths too, right? There was always Boolean logic, but on parallelly, we have fuzzy logic if you want to look it up. So there's always this fuzzy logic idea that, hey, it's not 0 and 1, but things are more fuzzier. So in fact, if you remember, or if you read about the history of humankind or human computers, before we had transistors, we used to have something known as vacuum tubes. So those were closest to the continuous model of understanding a human world. But then transistors showed up. Remember the same neat versus scruffy thing? Transistor showed up. Scruffy guy says, get it to work. It works. Why are we complaining? And in fact, if any of you is a musician, you will swear by what, like your amplifier is a vacuum tube. And any musician will swear on their life that the sound that comes out of a vacuum tube is so much better than a digital SSD, solid state device. Why? Because we are actually close to the human world of continuous music, continuous world. In fact, you might have heard of von Neumann architecture. Oh, by the way, this is a talk I gave at Oxford last week. It's probably up somewhere on the Oxford website, Oxford AI website. Anyway, in UK. But von Neumann architecture is basically the fundamental, this is probably how your computers look like. There's an arithmetic logic unit, central processing unit, input device, output device. So this was invented by a guy known as von Neumann, or suggested. But the truth is, he didn't give a damn about all this discrete stuff. Most of the work was in continuous geometry. In fact, he was the one who wrote Mathematical Foundations of Quantum Mechanics, which is a Bible in quantum mechanics. And this is 100 years ago, right? If not more. So I'm slowly introducing you to the world of quantum. And that is the one-line answer. That's my one-line spiel, which is quantum is continuous. It's not discrete anymore. We are slowly going towards that world of continuous learning, right? So in fact, if you look at the bag of words, it really is the last-ditch effort from the side of the scruffy guys. They're basically just throwing everything at the computer and hoping something sticks. Kind of make sure the more shit you throw, something is going to stick. And which is why you have ChatGPT. Doesn't make any sense why you need so much data to learn small things, right? So of course it works. But the truth is, or the simple solution is, we live in a continuous world. And of course, we need continuous tools to work on it. So quantum AI, or QNLP, is actually what we call the last bridge at the end of discrete world and the first bridge to the continuous one. Welcome to QNLP. In short, one line is QNLP is natural language processing and artificial intelligence and machine learning, all done on a quantum computer, right? So why does it work? For which you just need to understand this idea called qubit. And qubit is exactly like a classical bit. It has 0 and 1. But the 0 and 1 is only one of the petatrillion huge amount of possibilities for that qubit. If you remember your high school physics classes, remember there's a wave-particle duality. Particle is lit. So essentially their idea was, deep inside at the micro level, things are just a wave. Until you touch it, it collapses into 0 or 1. It collapses into a particle. The quantum computers have been trying to find this question that if I keep it in a wave stage and not touch it, I can just completely, I have a monster like that thing. You just need 2 qubits to learn the entire Shakespeare because it already has so much possibilities inside it. So that's what a qubit is. So a real life example of qubit. So the way they do it is, let's start with 1 qubit and call it, hey, here is an edge case. Let's call it hat, like edge case for meaning of a hat, right? So just keep that in mind, because next thing, what they use, the second thing, is known as entanglement. Now, you might have heard this word entanglement. It's known for the last 100+ years. And Albert Einstein, this is why Albert Einstein said God doesn't play dice, because here's the phenomenon. Let's say you have 2 spoons right next to each other. and you cast some kind of a magic. It's called entanglement. You take the first spoon, take it to the moon, leave the second spoon here. Now you turn the first spoon upside down, the spoon in the moon turns. This is what the Einstein said, there's no way this could be explained. People spent an entire century trying to explain this, and we still don't have an explanation of why entanglement happens. That's the physics world. Until like 10 years ago, the scientist Bob Kotka from Oxford, who my collaborator, he asked the question, all right, screw this. We know, I'm not trying to prove how entanglement works. What can I use it for? So now he started asking the question, if let's assume I can entangle two qubits, and they are so tightly integrated that you turn one, the other one turns. By the way, it's true. Right now you have qubits, one sitting in Earth and one in the moon. You turn one, the other one turns. People have no idea how this happens. It is reality. Look it up. So now he started asking the question, let's accept the reality. Qubit exists. How can we use that power to create a mental model, create an AI model similar to the original mental model? And his idea was this: let's build a collection of meanings. Like we start with a bunch of meanings like the hat, like assign qubit as a meaning. Let's start, how can we build it up? So what he said was, let's apply entanglement, or let's take two qubits, one for the word black and one for the word hat. Remember, I'm just building things up. Qubit for black, qubit for hat. And we have these words interacting with each other. And this is exactly how you remember Alice was initial mental model, Bob was initial mental model, Loves is another separate mental model, until in your mind, you started entangling them together and a new world is born. A new meaning. Oh, I didn't know Alice loves Bob until somebody told you that Alice loves Bob. Same thing. When you combine these words, they apply entanglement and voila, things just work beautifully, right? So remember, until 2010, humans have been trying to create all these models based on linguistic structure, which is we were neat people until the scruffies took over. And one of the reasons for that was human grammar is so complicated. Human language is so complicated. Sure, you can some way or the other take the definition of word from a dictionary and tell it to the machine. But the moment you start stitching it up into sentences, the classical machines could not do it, right? So because that's why we switched to the bag of words where we don't have to stitch it up. It's just a bag of words. You just break down the sentence. Now, QNLP went back and asked the question, why not build it up? Because now we don't care about hardware because I have a Q computer, right? Quantum computer. And then he arrives at the conclusion that grammar is what mediates the flow of meaning between the words, aka entanglement is what mediates the flow between the meanings of words. So we are actually going into a very intuitive concept of flow of meaning instead of flow of words. Like Alice, Bob, and loves, the moment you combine Alice, loves, Bob, there is the flow of meaning opening up the flower into a bigger pane of in your head, right? This is exactly the same thing I was saying. When you have a when you say the example of black hat, you understand these are just like adjective modifying a noun. But what if we just combine them together and entangle a qubit of black with a qubit of hat? That's the core part. Once you understand that, everything else is technology. Next thing they do is, oh, Alice hates Bob, so things have changed, okay? From 2 minutes ago, like Alice used to love Bob. So now there are tools now which can automatically convert those into quantum circuit. And quantum circuit is exactly like your XOR, X, AND, AND gates, NOT gate, everything. But now they are not at 0 or 1. In fact, what you see here, alpha A, alpha B, is the angle of the qubit. So literally, remember I said the qubit is 360 degrees. All it's learning is what angle it's pointing to. The first qubit is pointing to 365, the second one is pointing to 37. That's it. So you just need one qubit at the end of the day. Maybe basically the number of qubits is equivalent to the number of words. So that is also the caveat. At this point, the longer the sentence, the more number of qubits you need. So there's a lot of work going on there. But then everything else is exactly same. It just follows deep learning, right? So the feed forward back propagation thing. So this is how, the back of paper napkin kind of diagram for QNLP, like QAI. So it starts with a training sentence, and this is your goals label. you give, the theta is the angle. So basically you convert them into circuit, and this is a quantum computer. You give those to quantum circuits. So the first qubit is, let's say, Alice loves Bob, right? So you give it Alice loves and Bob as 3 separate qubits, and then you give it the sentence Alice loves Bob. So now it suddenly changes the angle from like 3 for these three words. Now you give it 100 data points about Alice and Bob, it slowly starts taking the meaning of the person Alice. Alice loves Bob, Alice likes to, play soccer. So slowly it's building up the meanings. And this is equivalent of what neural network is learning, known as weights. At the end, then, remember the back propagation, it just sends it back to a classical computer and says, do the stochastic gradient descent thingy, which is a pure classical math thing, because we didn't want to waste the huge capability of quantum computer to do that. It just does the stepping through. If you remember, there was a stepping through this funnel kind of picture I had shown a couple of lectures ago, and it sends it back in a feed-forward loop. That's it. It is exactly the same as deep learning. Instead of neurons, we are actually using quantum circuits. That's it. In fact, QNLP is the closest to how humans do learn a language, which is meaning of a word, build it up into a sentence, and let's show 1 or 2 examples, right? If you really want to know about Alice and Bob, or Alice as a person, you really need only, let's say, 100 examples about the personality of Alice, and you can ask a question about Alice. Same thing as bank, right? I went to a bank to withdraw cash. I went to a bank to catch some fish. So you're slowly developing the meaning of bank based on the examples, not bank based on the words around it. In fact, this is one of the questions they had asked the QA model, the question answering model of the IBM Quantum Cloud. And the question was, is Chomsky an anarchist? And it said yes. I mean, after feeding it all the Wikipedia data about Chomsky, right? Not sure you know, Noam Chomsky is actually in University of Arizona. He's an emeritus professor. If you visit the linguistic website, if he's giving any talks, I don't think he is. Now, my research is so my thought was, hey, sure, it's a good idea. You're doing all this in classical computer, but remember, we already have this huge amount of learning or knowledge that is coming from large language models. So why are we going orthogonal to it and saying, completely ignore the huge amount of learning? Let's utilize it. Let's feed in the knowledge from LLM also. Can we do that? And the way I have been doing it is, I take the LLM, the embeddings of each of these words. If I give you the sentence, Alice loves Bob, I do not directly throw it into the quantum computer. Remember, this Alice loves and Bob needs a qubit to be initialized. Or in other words, let's say Alice is a qubit. And right now it starts at 0, or whatever is 0, right? So whatever is 0 in 360. Eventually it learns from those 100 sentences that, oh, it first went to angle 37, then to angle 132, etc., etc. And all I'm saying is, instead, we initialize it exactly at the point where the classical machine is learning it, and let's see what happens, right? So to prove, the proof is in the pudding, right? So the idea, like I said, is take the rich meaning learned by LLM embeddings and use that as a fundamental block to build meanings in a QNLP pipeline. And the proof is in the pudding. I took the same experiment, like train only on 100 data points, and let's ask it to predict, hey, what kind of a guy is Bob? Like, does Bob like to smoke hookah? Remember, we asked this question to open source large language models, training from scratch. It was 0.4 and 0.3. And ta-da, QNLP model gave perfect accuracy, because it's really just needs 100 data points to understand the personality of Bob. Now, sure, if you ask him about President Barack Obama, it has no idea because it has not seen Barack Obama. It might give you exactly the same answer which ChatGPT gave because the embeddings are sitting from there, but you're not fine-tuning or training it on anything specific. So I think this is very important because, right now we are going towards this weird stage of 1, dependency on paid models. So that is terribly bad for students. 2, privacy. Like every prompt you type on ChatGPT, it's really learning your private data, especially like you want it to learn from emails. It's going to take, give me the emails, I learn, but it's probably sending it to a server sitting somewhere. So the idea is, how do humans learn language? And this is exactly what we have been doing. By merging LLM, the classical and the quantum world, we are at the last bridge or the border between Q and C, quantum and classical. Last 2 minutes, I will talk about the crazy shit I'm doing. I call it fool's rush in where angels fear to tread. Not sure you have heard of these people, Roger Penrose and Hameroff. In fact, they came up with this whole idea of quantum consciousness, or why are we conscious? What is the meaning of consciousness? And their idea was humans are really waves. Remember the wave particle duality. And it's the consciousness which is keeping us in this body. Because if you sleep, you know you're in a different wave kind of form because you're actually flying around. Your body is here, but your consciousness is somewhere else. You're dreaming. And they came up with this whole idea that this is a quantum phenomenon, just like a wave particle duality. You are a wave until you wake up and your consciousness collapses into the particle or the being that you are. This is actually from 1960s. It's a well-known paper created right here in University of Arizona because Hameroff is a anesthesiologist, by the way, and he knows a thing or two about consciousness because he has been, putting people under or putting them to sleep for all his life. And that's where the thought come up with, hey, what is exactly consciousness? I mean, how are they waking up, from surgery, have no memory, why can you just not be putting them to sleep? If you are, let's say you give them a high dose of sleeping pills, they wake up when the knife cuts through. So how is that different than any of the anesthesia that you give them, right? And their answer was, stuff doesn't happen in the neuron, stuff happens in one level deeper, known as microtubules. Remember, the whole AI was built on the idea that all the stuff or intelligence happens in neurons, but an anesthesiologist says, no, it happens on microtubules, which is one level deeper than the neural network, in consciousness and intelligence, right? And his theory, you can look at the theory, it's called ORC, OR. And his idea was, like I said, you are a wave until your consciousness collapses into a particle. And I am asking the question, can we reconstruct microtubules using quantum circuits, which is actually, the real neural network? That's what they call it. Like neural network sure is great. And if you can do this, the GPT thing with just by trying to mimic neural network, imagine what it can do if you can mimic it in the microtubule level. And remember, we are not at the discrete tools anymore. Like if I was trying to mimic microtubules with the classical circuit, I would have failed. I'm pretty sure I would have failed. But now I'm using a quantum computer to do that. And let's see how intelligence learns. So that is the end of my talk. Oh yeah, consciousness.arizona.edu if you want to really, don't read this before sleep. That's all I will say. These are very important questions, and this is happening right here in Arizona. So anyway, that's the end of my talk. And the next slide is fine-tune Llama, but we are like 1:50 p.m. and I'm probably gonna have confidence on you guys to do it on your own. Meanwhile, maybe I'll just go through it. While I click on this, I will open the floor for questions. Questions in person, on Zoom, or I don't even know if the chat has questions. Let's see. Chat has no questions. Sure, here's a question in person.
I guess personal question, what are you working on specifically with QA right now?
This stuff, I'm basically trying to recreate that 100 data points experiments. If I can prove that, that's basically, I can extend it to 1 million, right? So that's the same data point. My thought here is we probably don't need a huge machine and so much amounts of data when all you need is one quantum computer. Oh, by the way, there are 3 ways of actually talking to a quantum computer. You should look it up. There are actually probably 4 or less than 5 companies in the world which has its own publicly available quantum computers. Google, Microsoft. I don't think Facebook has it. There's IBM quantum computing, and also Quantinuum, or which is just taken over by Honeywell. All these guys actually provides you interfaces just like your pip install stuff to run stuff on quantum computer. But of course, then you walk into this whole scheduling nightmare because there's so many people who want to run on quantum computers. So they provide simulations of quantum computer, which completely runs on your laptop or your high performance cluster. And all my experiments have been done there. So you really, if you are interested, you should just Google IBM Quantum or publicly available quantum cloud. IBM is actually much better in support at this point. And yeah, you can just start posting stuff to quantum computer and ask questions and learn something, because that's the future, I think. You should never prepare for today, because today was invented 20 years ago. Yeah.
Cool, thank you.
I mean, for the rest of the time, I can just click on all this stuff if you don't have questions, or I'll just wait for more questions. I think we are right now. Sure. A question here in person. Yeah.
Okay, so there's like 5 companies that have quantum computers, and they are making it available for limited time for public users. How far away is more like massive deployment, massive manufacturing of this?
Oh, I'm gonna say decades away. Yeah, so the quantum AI is not gonna kick in until you have, like I said, things are invented 20 years ago, which you're seeing today. Like ChatGPT was not invented today, it was invented in the 1960s, the fundamental models. So by the time the scalability and practical, all these proof of concepts are great, 100 data points, I cannot run it on 1,000 data points because there is not enough qubits publicly available, right? So that it's not gonna take a year or two, it's gonna take decades before this becomes publicly available. And in fact, NLP, I can probably show you this LAMBEQ. This is the only model which converts plain text to quantum circuits. Like, this is it, that's it, right? This field itself has existed only for 2 years. And this model, Llama, is the only one in quantum AI. I mean, there is Google doing some stuff in quantum AI, Google research, but that's hardcore hardware. They don't have a publicly available software model, right? So you can talk and write circuits, but you cannot give it a sentence and that converts it to circuits. So if you're interested, this is a company like I hang out at, work with, push my stuff, Quantinuum. And Llama is the tool they developed. And this is the same thing I was telling you about. Give it a sentence and it'll give you, throw out all the quantum circuits, which you just take it and post into your quantum computer of choice. But yeah, this is very limited right now. Oh, I forgot. The other caveat. These machines, especially this tool, really requires well-established, well-written sentences. Because remember, grammar, we thrive on grammar. It needs subject, verb, object if you're dealing with English. But colloquial language doesn't really always use that. So which is why, like, colloquial language doesn't always subject, verb, object, You say, it's rad. Nobody knows what rad means. It doesn't have subject verb. I mean, probably it does. But anyway, the colloquial language is so much different. So this one actually throws out sentences which is not well formed. So even if you give it 1 million sentences, you get like 20 out of it saying, hey, these are the only well-formed sentences because this is not grammatically written. So there is that mountain to climb. But hey, it's a fun experiment if you want to just play around with it. Okay. Does it answer your question? It's not in the near future, no. It's a very interesting, promising start. Yeah, let me just just quickly at least run you through the code. This is like, remember I was telling you in the last class or a couple of classes earlier, we created a chat model based sitting on top of Llama. This one is just instead saying, hey, okay, you learned everything from the internet over Wikipedia. Let's fine tune it on data which I only have. And this is very important because, medical data, you don't want it to leave your premises, but yeah, so sad it still does, even with this, but that is the kind of use cases people have been thinking about. Same stuff, pip install, a bunch of these, you've seen all this auto model, auto tokenizer. Bits and bytes are more like a GPU thing, faster. So, and your, same Hugging Face-based model, which is why I introduced you to Hugging Face in the first place. And you're getting Llama 7B, assuming your CyVerse uses it, or you already have a Jetstream account. Kind of same thing we saw earlier, model, auto model, create the model, create the pre-training configuration. Padding, you don't have to even know what that is. It's basically just adding zeros if the sentence is smaller than 256. Nothing interesting here. This is their own trainer for that pre-trained model. Everything goes fine until, where is the, all right, let's go to the actual references. And the slideshow. So much for technology and quantum advancements. Okay, this is the place I was referring this from. So basically they are using the same idea. Let's look at the code. Pip install all this stuff. So yeah, this is all technical stuff. We'll run out of the box. Llama, you load a tokenizer, and we saw all these training parameters. And here's interesting, but the fine tuning, right? SFFT is the fine tuning model. And this is basically like you are already providing this smaller data set, right? You're giving them this. It's so easy. You just need to provide it the data set you want to fine tune, and an SFFT trainer from Hugging Face does that for you. And that's it. So I think my code was right, because all it does is finish the SFFT.trainer and .train. Yep, the code was right. So it just trainer.model, trainer.save. So that's all you need. Like, this is all evaluation and testing. And you just have a model which is fine-tuned on your local data. Of course, it opens a can of worms, which is like, hey, how do you know this data was not seen before by GPT? Because anything GPT or Llama trained on, we don't know what it trained on. And we had this interesting discussion earlier after one of the classes, like, Steve Martin, who's the guy who wrote Game of Thrones? R.R. Martin. Okay, R.R. Martin, suing GPT, saying, how are my copyrighted text? How does GPT know about my copyrighted text, right? So we don't know if the model has already seen this. So you probably should run this model and test it before fine-tuning it on your data and ask the questions, hey, do you think this rare disease has this rare symptom? Have you seen this before? If it has already seen, there's no point fine-tuning it, right? So it's a very thin line people have been trying to straddle. It's a big can of worms, don't want to get into. But that's it for today. You'll probably get a feedback email. Please, it's a minute-long survey. Just take the survey. It asks you what is one good thing or one bad thing. I don't care if you tell me the good things, but I would rather you tell me what are the bad things, or what things you would want to see in this kind of a setup, a workshop series in the next semester. Like, clearly you guys are not going to be here, but what did you feel like? What was missing? And remember, we are a horizontal department. Our goal is to take AI to the masses, not just computer science, anybody who is not a computer science department. And this is the whole goal of the workshop series. So give me a feedback. In fact, I think we already have the forms sent out. Yeah, I'll send it to you in email. I think you guys have already been getting emails from me.
Okay, can I add something?
Yeah. Or let me
We're-
do it. Otherwise it's
Yeah, it's okay. It's okay. So we're in planning stages for next semester. We're going to repeat a similar workshop in deep learning, and also we will add new materials. So you will find the information in the events calendar from the Data Science Institute. So I hope we will see you again next semester for new workshops. Thank you for attending. And this was our last session for this workshop. And well, good luck with your finals, and hope we see you next year. Thank you.
Thank you all for suffering me for a whole semester.